Okay, so for the second essay, we're going to begin talking about pressure volume loops. And so I'm going to draw a little graph here with our volume and our pressure. And so this is going to be with our left ventricle, and so our volume doesn't really change too much. So it's going, and then we'll have a dramatic increase in pressure, and this is our EDV, so our end diastolic volume. And then we have our semi-lunar open, and then like 50, we have our ESV. And so let's say we want an inotropic loop. So that deals with the steepness over here. So let's say we have this line and this line, A and B. A is going to be steeper, so that's going to increase our inotropic. So that's going to be our contraction. And then let's say we come over here and we have preload, and preload deals with the volume before it enters the aorta. And so our pressure is going to be increased, the pressure is increased. Which is going to increase our cardiac output. And then finally, let's say we have a greater volume. This is going to be afterload. So an increase is going to cause our graph to look like this. And so this is afterload explaining like how much pressure is needed before the door can open, and that sums up our pressure volume loops. Okay, so now we're going to talk about something that is very important called baroreceptors. And the reason why baroreceptors are so important is because our brains are constantly needing blood and our cardiomyocytes, and if that doesn't happen, then we are at risk of something that is not good. And so for our baroreceptors to happen, I'm going to draw a heart. And I'm just going to draw our aorta. So we have our carotid artery here. And so we have our brain. And I'm just going to draw our kidney. And so we have right here a signal. This is our cranial nerve 9. And then we'll also have our cranial nerve 10. And so that will get sent to our brain. And then from our brain, we have what could get sent back to the heart. Two different signals. We have our parasympathetic nervous system and our sympathetic nervous system. And so this will slow our heart rate, and this will make it go faster. And then we could also get sent to this little part in the kidney called our adrenal medulla. And then from there, it can release epinephrine and norepinephrine into our blood, which is going to decrease our venous return, which is going to decrease our cardiac output, which will decrease our heart rate. And then we also have another one here which will go to our veins and cause venous or vasoconstriction, which will lower our blood pressure. And so that is our baroreceptors. And something else that I need to mention is a concept called MAP, which is our mean arterial pressure. And so to show what that is, I'm going to draw this graph. And so we have here our pressure of 120 over 80. And as we go through our arterials and veins, it goes like this. So this is what our pressure would normally look like, and so our MAP pressure is just going to be the average of that, which will kind of look like this. So to calculate MAP, it's going to be our cardiac output times our peripheral resistance, and that determines our MAP. Okay, so now we're going to talk a little bit about how blood flows through the capillary. So I'm just going to draw a capillary here. And so we have our arterial end and our venous end. And the blood is going to flow differently at each part of those. And so to begin, we'll have this thing right here that we call our precapillary. And that, if our MAP increases, this is going to increase as well. And this is going to be a pressure of 160 millimeters per mercury. And so we have, I should draw our tissue cells here as well. And then we have lymph nodes. And so if we're here at the arterial end, we'll have our blood pressure, and that will be, I'm going to draw them over here, 30 millimeters of mercury. And then we'll have our ICOP, which is 8 millimeters of mercury. And then our BCOP, that's going to be the only one that flows in because of the protein albumin. And so BCOP is there. And then we have our IFP, and that's going to get eaten up by our lymph node over there. And so our IFP is going to be 3 millimeters of mercury. And so that's on the arterial end. So if we add those up, the ones coming out, so these are out, and then in, if we add those up and take the difference, we're going to have a net force of 13 out. And so this is very similar on this end, so I'm just going to draw these same arrows. So our blood pressure, the only thing that's going to change is our blood pressure, and that's going to be, now it's going to be 10 millimeters of mercury. And then we'll still have our ICOP and BCOP, and our IFPs over there. So that's going to be 8, 28, and then our IFP is also going to be 3. And so now we have a net force of 7 in. So as you can see that they're pretty similar, but little bit things are happening. And the reason that the blood pressure is decreasing is because of the friction that is happening as it's going along. And I don't know why that's not working. But now we'll talk about an example of what would happen with edema. And so let's say our mean arterial pressure, or MAP, is steadily increased to a rate above this 160. That's annoying. So if that is increased by 160, our hydrostatic pressure, which is our blood pressure, and our IFP, those are both going to increase. And so we're going to have more fluid on this outside here. So we're going to have more fluid, and that's going to cause edema. And so one example that could cause edema is if this MAP pressure, if our MAP is steadily increased above 160.